So the next talk here is from Joaquim Rocha from Igalia. He's from Portugal, and he will talk. He has worked on some applications like the BluePad, a Java 2 mobile application for PC remote controls. He has ported the Eye of GNOME tool to Maemo. He did an app for tracking TV shows on the Maemo 5. And as his master thesis, he wrote some tool called OCR Feeder, which converts printed documents into an open document format. So, and now he's talking about a skeleton tracking framework. This was made because the Xbox device, the Kinect device from Microsoft, was the first camera on the market which was cheap to get and provided you dev informations. But there were only closed frameworks for more complex work with this information, and like skeleton tracking and so on. And so he developed a library called Skeltrack, or a framework. And now he talks about this library. Warm welcome to Joaquim.
Okay, can you get me a water?
Yeah, I try to get one.
Okay. Hey guys. I was already introduced. I'm Joaquim. So I work at Igalia. It's a company in Spain. It's based in Spain, but it's joining hackers around the world. It's just it's a free software consultancy, the company, if you want to check it out. Anyway, so just like you said, I worked on OCR Feeder and also a program called Series Finality Track Series, because I like doing innovative stuff, something that just tackles a need, a problem, like I think we all like to do. Last year I was here introducing OCR Feeder, and I really liked the feedback that I had from German folks. And today I'm going to present this Skeltrack thing. So first let's talk a bit about the Kinect. So the Kinect was the first camera with a price affordable to the public, the first depth camera that people could afford, because it's just over 100 euros, and almost every developer can afford that to hack. So one good thing is that Microsoft, they said it was all on purpose, but the USB connection of the Kinect is open, so you can get the signal and you can do stuff using libUSB with it. So I think I heard that in the beginning they didn't like really that people hacked the Kinect, but then they saw the tremendous success that it had, and they said, oh, we left it just like that on purpose. So I don't know which story to believe, but anyway. So because of the connection being open, it originated open source projects like the libFreeNect, which allows you to control the Kinect using this independent library, not from Microsoft. And you can use it on Windows, on macOS, and on Linux. So in Igalia, we do a lot of work in GNOME, and we like the glib library. Thank you. So we developed a wrapper around libFreeNect to be more friendly with the way that we do stuff in GNOME. By the way, who knows glib or have used it here? Only one person. Two, okay, three. Well, so we developed this wrapper, and it offers some nice stuff like an asynchronous API, which is cool because it won't block your UI when you're trying to connect with the Kinect. So yeah. We also have some synchronous functions because, for example, one of the functions, one of the things that you can do with the Kinect is that it has a tilt. It's called a tilt, which is a little engine that makes it go up and down when you put it on top of your TV or whatever. So we have an asynchronous function for that. So you just say, okay, put me the tilt at 0 degrees, and if it's on 30 degrees, which is the maximum, you do not have to wait because it's asynchronous, so it will do it something like zzz, and then you will have a callback when it finishes. But sometimes you don't want to do that. If you have a command line application, for example, you just want to wait until it's on 0, so we offer some synchronous functions as well. One good reason to use glib is that it offers you G-object introspection. So G-object is like the base for every object in glib. So glib kind of offers object orientation on C. And the G-object introspection, I don't know if you know about it, but it's really interesting because before you needed to do a binding for every library that was written in glib. And right now with G-object introspection, you just need to do the bindings for the languages you want, but you do the bindings for a glue code that will load other libraries by itself. So in the case of Python, you got the PyG object, and that's the piece that people need to do the bindings by hand. But once that is done, and it's done, you can load libraries dynamically on C. So this is like free bindings. And you can use it on Python, on JavaScript, and on Vala. Vala is kind of a C# language for GNOME. So some people think that the Kinect is a stereoscopic camera. Stereoscopic would be like we humans do. We have two eyes, and our brain just do the calculations and says, okay, so I'm looking at this microphone, and it should be around this distance because I'm used to things being this distance, and I can compare all inside my brain. So the Kinect does not do this. The Kinect, what it does is that you see the circle on the left, on the farmost left, that emits an IR pattern, a light pattern. So the light then reaches you or whoever is in front of the camera. And the rightmost circle, it's an infrared camera. So that captures it, and the Kinect just sees the distortions in the image, and from that it can calculate the depth. The circle in the middle is a regular RGB camera. So people usually think that two of those cameras are the stereoscopic thing, but it's not like that. And this technique is called structured light camera. Okay. But anyway, that information that it does is just raw values from 0 to 2048. That's 11 bytes. So I'm telling you this because people usually think that the Kinect already gives you the skeleton thing. My brother used to attend computer science. He's now moved to be a male nurse. But he watched the video I did for Skeltrack, and I asked him, so do you think it's cool? And he said, well, it's pretty cool. What camera did you use? I said, I used the Kinect. And he said, so what did you really do? Because the Kinect already does that. The Kinect does not do what I'm going to show you. The Kinect just gives you information about what's closer or what's further. And the libfreenect, and of course the wrapper we did, the gfreenect, can give those values in millimeters. So this is what you usually capture using the gfreenect. That's me, by the way. So it's kind of difficult to see because it's in grayscale. But what I did was to put a threshold. So it didn't capture the walls and the chairs and everything that was in the office behind me. But it just captured like a threshold. And it's difficult to see, but that upper hand, it's closer to the camera. It's like this than this one. So it should be darker. But I think you cannot really perceive that from that. Anyway, this, what you just saw, does not tell you that there is a person in the picture. It also does not tell you it's a cow or even the implement, let alone a skeleton and where the joints are. Because for that you need another piece of software on top of this, which is called a skeleton tracking solution. So as always, you have proprietary stuff to do that. So let's do a bit of commercial work for Microsoft. And you got the Microsoft Kinect SDK, which is for non-commercial work only. So that is, if you want to develop business using this SDK, you cannot. You can just do it for your independent or student stuff, because if you want to do money, if you want to create value with it, Microsoft wants a piece of that. Then you got the OpenNI or OpenNI or whatever. So this one is more open, as in the sense of they have parts of the, this is like a framework, and they have parts that are open, and it's commercial compatible. The problem is that it's got some binary blobs that you need to install, and you need to accept an EULA license to use the skeleton tracking part. So yeah, not enough for me. And recently, Microsoft released what they call the Kinect for Windows, which is a commercial, it allows commercial usage of it, but it's incompatible. I don't know if it's incompatible in the technical way or just in the legal way, but it's incompatible with the Xbox Kinect. So what it means is that you need to go to Microsoft or to their providers and buy a Kinect that is a little bit more expensive than the regular one. And here's the share that you need to give to Microsoft, because you're going to do commercial work with it. Sorry. And of course, Microsoft does not really care about us who use Linux and other stuff. So it's only for Windows, and that's unacceptable. So the conclusion is there were no free solutions to perform skeleton tracking. So we decided to build one. I think this is the way that open source works and should work, is that you see something that you are not satisfied with, and you should try to put your skills to work into it, even though it's not really as easy as sometimes it sounds. So what we wanted was a shared library. By the way, as I said, it's called Skeltrack. And we wanted a shared library. No fancy SDK. It's not even a framework like it was introduced, but no problem. We wanted it to be device independent. So I gave you all this lecture about the Kinect for a reason, which is if you are going to hack on something with a depth camera, it's likely that you are going to buy a Kinect unless you have more money to spend on another. But we wanted to make it device independent, not like the other solutions I told you about, which expect you to connect a device to it. We expect non-device to be connected. So we also didn't want pattern matching or databases, because that's another complexity to the whole thing. And of course we wanted it to be easy to use, because everybody wants that. And this of course is not really straightforward. So I was researching about it, and I found this paper by a German researcher called Andreas Bach. And it's got this very descriptive name. So we based our work on it, not completely of course, because this paper uses a database of poses. So they capture, we do more or less what they do that I'm going to explain, but once they know where your points of interest are, they match them with a database, and they say, okay, so this guy looks to be like this, or this guy looks to be like this. That's pretty good, but I don't know how it goes when you need real time. So how does Skeltrack really works? First we need to find the extremus. The extremus is like if you imagine a starfish is like this, right? A starfish, the extremity of the starfish is like this and this and this. So it's the points. You can say that are the points far away, further away from the center. So to get the extremes, we first need to make a graph whose nodes are the depth pixels. So we take the depth buffer that the LibFreeNect or another library gave you from a 3D camera, and you make a node of it. The way to make a graph, that is, of it. The way to make the graph is that the nodes or the vertices should be connected to each other if they're neighbors, and I look for 8 neighbors, if they are less than a given value. If they are too far away, like this point is too far away from this point, I do not connect them. But I connect this point with this point with this point, and so it goes. So another thing is that the Kinect, I don't know if you tried it with a LibFreeNect, but it produces a lot of noise. So I don't know if you saw on YouTube or something that you see the depth map, and it's always like flickering. And that's because of the light stuff that I told you about. And also there is another thing to consider, which is when you, for example, you are like this, you have an arm here, there is an area below your arm that is completely black. And by black, I mean that the Kinect doesn't know what's there. And that happens because you're creating kind of a shadow to this part. Because you know the light comes from one place and the camera captures it from a slightly different place, and it produces shadows. So this means that we sometimes end up with 2 components of a graph, and that's not good. So we need to connect the components. So if I'm like this, I have a component which goes from my arm up and another component that goes from my arm down. And the same happens when you are like this, you can have a component just for your hand. So you need to connect them. So the way to connect them, that is from the paper from Bach, is to get the closest points to the component that has the greatest number of nodes. So if the greatest number of nodes is my torso, and I'm like this, and this is a different component, I connect the closest points of this component together with this component. So I just draw an edge from a point here to here. Anyway, don't worry about the math. So, yeah. So then we need to choose a starting point and to use the Dijkstra's algorithm. Dijkstra's algorithm, as you might have studied in computer science, if that's your background, is an algorithm to calculate the shortest path between 2 nodes in a graph. So we need to calculate this from a starting point to every other node. And then we choose the furthest point. And that means that you get an extrema. So what it means is that if my starting point is this one, and I'm like this, I choose the point that is further away, and it of course will find my leg, in this case, or if you are seeing just from my waistline up, it might find my arm, because it's the one that is further away. Okay, so once we find those extremas, what we need to do is to connect them with the point where we started from, and we connect them with a zero-cost edge. What it means is that, what it means is that the next time you calculate Dijkstra from the starting point, you will no longer get the same extrema because you already have a path to that extrema that costs 0, so you'll be like that in there. So this means that you will not have repeated extremas, okay? Once you have that, you also change the starting point. You say that the starting point is now the extrema that you just found. And this means that if my starting point was this, and the first extrema was this, and I am like this, the second extrema will be this, because it's further away from both points. And you can do this n times to find n extremas. So the first difference from what we did to Bach's paper is when choosing the starting point. Box chooses a starting point that is a centroid point. The way to do this, you can do it in many ways, but one way of doing this is to get an arithmetic average of all the points, and then you get your centroid. But what it means is that if you are like this, you get a centroid that is, if you are calculating from the whole body, get a centroid that should be like this. But if you are like this, your centroid will go up. So we first wanted to focus on the upper body. So this means that if I am like this and I get the starting point here and I start calculating extremes, it's okay. But if I do this, my centroid point will go up, and this means that points below will be farther away, and that I will have more trouble to find the upper body part, which is the one I'm interested in. So what we do is that we calculate the centroid point, and then we choose the point that is lowest vertically, but horizontally aligned to the starting point. That is, if I am like this, and I'm recording the whole of me, I get the central point, the centroid point, and then I calculate the one that is below until I don't have data. So it would be my fit. If you are calculating from my belly up, it would be around here. And this is good, because this assures that you will always get the extremus up in your upper body. I don't know if you are understanding anything, but we can talk later. So you do all this and you got the extremus. So what to do with them? Because, okay, you know that there is a point in there that might be a head, that might be a hand, that might be a shoulder. You don't really know. So you need to interpret them. And the way we do this, unlike Bach, who uses a database, we use heuristics in this case. So these are just educated guesses that work for most of the cases, we hope. So anyway, rewinding a bit, we do the algorithm to get the extremus for 3 extremus. Why 3 extremus? Because we are focusing on the upper body, and the upper body has 3 extremus, the head and in both hands. So the next step to identify them is to check each of them and to hope that they are the head. The way we do this is that we go through each extrema and we look for the points where the shoulders should be. This means that if the first extreme is this hand and my hand is like this, for example, I go here and I say, okay, so the shoulders should be around here, and here, and you do not have data in there. By the way, the values of these 2 imaginary shoulder points are configurable. So you do this here, it will fail. You do this here, it will fail. You do it to the head, and you get the shoulders. Of course, that sometimes, if you are like this, you might get one shoulder here and one shoulder here. We are trying to tackle that one. So if they obey these rules, you get the head and shoulders. So about the remaining 2 extremas, you also need to do some work, because they might be hands or they might be elbows. Why is that? Because sometimes you are like this, and of course, if you are calculating from your starting point here, it will not give you the hand. It will give you something farther away. But we saw that, for example, a usual case is that when you are like this, and the furthest point are the elbows. So to see if they are hands or elbows, we calculate dijkstra from the remaining extremas to the shoulder points. In this first step, for example, I calculate from here to here, and I get a distance. And I also calculate from here to here and to here. This means that I do this for both shoulders and not just the shoulder that is horizontally aligned with the extrema, because if you are like this, it will say that this is my left hand when it's not. And by doing dijkstra to the shoulders, you will get that fixed. So about the hand and the elbow that I was explaining, once you know that an extrema is the left one and the right one, what we do is that we check if the distance to the shoulder is less than a defined value, which can be changed as well. according to your needs. So if it's less than a value, for example, or if it's further than a value, like if it's further than this, for example, I say, okay, so I got a point here, and it's greater than this distance, so it's not an elbow, it's a hand. But if I am like this, and I get the extrema here, it will be an elbow. Still, if you find a hand, we still need the elbow. So what we do is that we use the path that we calculated before from the extrema to the shoulder, and we check the point that is close to that elbow distance. So it will always give you a point that is really close to the elbow, this way. And you got yourself skeleton tracking with this. So, but there are some things missing. So this will be the future work. Of course, if you get the elbows, I still do not find the ends this way. So I need to do something for when you are like this. I need to check, probably abusing Dijkstra's algorithm again, to check where the hand is. And the problem with this is that I need to check that it's this way and not this way, for example. Also smoothing. So because of the noise and all the things, you get a lot of jittering in the extremas. This also happens in OpenE and also Microsoft's SDK and all of that, and they have values to tweak this to just make it a little better. So I need to do that as well. Robustness. We need some restrictions because right now, if you have a chair next to you, it might be considered part of your body. So we need to do something to exclude some elements. And multi-user, because right now we track one person. It will be fairly simple to track more than one person. And of course, get the rest of the extremas, of the joints, sorry. The knees and the feet and all of that. So how to use this? You got the asynchronous API that we did for this. So how many people know C here? Okay, quite some. Okay, so we just initialize a skeleton instance, right, on the first line, and then we call the asynchronous method track joints. We give them the skeleton, we give them the depth buffer. As you see, there is no Kinect involved here. You have to give, of course, the width and the height of the buffer. The first null argument, it's a G-cancelable. It's part of glib's API for asynchronous functions. So I have a null in there. It means that I do not have a cancelable function that I will call to cancel this processing. And of course, I give them my callback, that is the on-track joints, which will be called once the joints are tracked. The remaining argument is null because I do not want to assign any errors, any error variable. So you define your callback on-track joints. It has, of course, some predefined arguments. Then we initialize some joints, and we just declare a list. And the way to get the list of joints is by doing a skeleton track joints finish. And it will get you a list that might be empty or not, if you have a person or not in front of the Kinect. And then if you want the head, for example, you just need to do this to the list. List get joint, and you pass it the head ID. And the same for other extremes. So we also have a synchronous API, which with just this call, you can do skeleton tracking. This is good for offline processing. There is a Greek company that is using the synchronous API. So a skeleton joint currently has these many variables. It has an ID to identify if it's a head, a left elbow, right elbow. It has an X and Y coordinate in the real world in millimeters. And it has a screen X and screen Y coordinates, which is in pixels because you might want your values in pixels to draw something on screen. So if you want to submit patches or open issues, you got the GitHub. in there. You also, if you want to develop with it, you can get the GFreeNect, like I said, and I developed also something called GFreeNect2012, which is cool for developing. So this is the GFreeNect Python example. It's written in Python, and you can control the Kinect using this. It's part of GFreeNect. This is one of the nifty tools that is part of GFreeNect-utils, and it's a record depth file. Well, actually, I'm mistaken. So this is the depth file viewer. You just pass them a depth file, and you can also give them coordinates to be put in there. So this is cool because you can use the Skeltrack, get the coordinates, and just check where they are without rendering it on real time. And this is the record file depth file. This is a colleague of mine, the one that developed GFreeNect. And you just launch this, and you see how you look in there, and you press space to take a shot of you. So it will record a depth file that you can view with this. And that's it. We got no more time, so questions?
Thank you very much for this interesting talk and this interesting work on this closed device. So, any questions? No questions at all? Is that possible?
Oh, by the way, I've got 2 Igalia mugs for the best question, so you might as well do one.
So your work is related to a very simple body model, and for example, if you want to take a picture of your cat or your dog, this would not fit.
Of course not. By skeleton tracking, I mean human skeleton tracking. So.
And what happens if you have a tool like a stick or something for a basic game? Is it possible to distinguish the stick from an elbow?
No, not really, because we're just aiming for people to do the stuff that they usually do with the Kinect, and I'm not even talking about gaming only. You might, for example, have an architecture firm. You want to show models, 3D models to your clients, and you can use a Kinect, use Skeltrack, and you just rotate them like this or wherever you can. Oh, I got some videos to show you. I don't know if there is time or not, but it's 1 minute.
Yes, you can show it.
Okay, so yeah, I almost forgot. So let's see. How much time do we got? Oh, 4 minutes, that's more than enough. So this is the Kinect test that comes with the library. And as you see, this is real time. I swear to you, this is not post-processing. I do not usually only wear this t-shirt, but it's just coincidence. So as you see my hands in there on the left, the circles kind of are bigger when they are closer to the camera. What's going on? Yeah, so you can see that the circles are slightly smaller when they are far away, and bigger when they are closer, right? So this is kind of interesting, but what people really liked, and that's the reason this appeared on Ars Technica and PC World and Slashdot and whatever, is this video. How many people saw this already? Nobody? All right. So this is the GNOME desktop, and I just did a small piece of code on top of Skeltrack to control XLib. I connected to GNOME 3, and you got a desktop like Minority Report and stuff. This is also real time. You can see the Kinect here in the right, and this is just a regular TV that we have in our office. No, the code uses xlib, but just because I had to use something to feed GNOME with the events. So it's really simulating a mouse, right? And you can, when I do pinch, I just simulate the mouse wheel up, control mouse wheel up. You can do questions if you want.
Actually, do you have a plan to recognize if the person is looking at you or looking away from you?
Sorry?
If you have the skeleton, you have no information if the person is looking at you, at the camera, or if it's looking away. It's about the same. If I'm looking towards the camera or away.
No, because we do not track the face. That's actually one of the things I need to consider. Like when I get the Extremus, probably it's a good way of making it more robust. Just to use OpenCV around the Extremus area and to do face detection. So of course a hand will not be positive when you are looking for a face. In this way we could be always certain that it's a face when we're looking for it. Yeah, so you can also play games in Linux using this.
Cool. Are there any more questions? Okay.
Actually, you say real time. How small can the hardware be to have the information real time? Actually, a little ARM box with 400 megahertz will they be able to give you?
Talking about the minimal specs?
Yeah.
I don't really know. This is running on my laptop. This one. So I really don't know. It's a matter of trying it out. Anyway, I did this, of course, because there were no solutions, but because we have a small team in Igalia that is trying to get into interactive installations using free software. So we will try to run this on minimal hardware. It's not going to run on, I don't know, Arduino, I assume, but but yeah.
Any more questions?
I can tell you also that the funniest case, I received a lot of emails because of this, and the funniest case that somebody asked me about was that it's a researcher in Costa Rica, I think. He said that he's tracking monkeys in a zoo or a forest, I don't know. So he tried to use OpenE and it didn't work because they are slightly different than us. He tried to contact the OpenE guys, no answer. He tried to use Microsoft, he couldn't. He tried to contact Microsoft, forget about it. So he's trying to use this to track monkeys, which is something I didn't imagine.
Okay, so thank you for this interesting tool and this interesting work and the talk here. Applause please for Joaquim. The next talk